Let's from Stanford, who will tell us about the uses of wormholes.
Thanks, Eric. Thanks to Nick and Yosef for inviting me to Paris. It's my first physics visit to Paris ever in my career, and I'm having a very good time so far. I thought I would take this opportunity to try to speak, try for us, the fuzzball community and the wormhole community, kind of to try to speak the same language, or at least try to understand the concepts that both communities are trying to grapple with. But I feel like in the past, I have not had this opportunity to interact with the people in this community one-on-one. So I thought this would be a good chance to do that. So that's why I chose a survey talk. It's a survey talk, which means I'm just going to be talking about past results and mostly other people's results. This is not a talk about my work or something like that. It's just the story that has emerged. But a lot of people are at Stanford, so I talk to them a lot, and I kind of know how they think about things and stuff. So I thought maybe I would, take this opportunity to present things. So I'm a postdoc at Stanford, and the title of my talk is copied from Coleman's chapter in his book Aspects on Symmetry. The last chapter of that book is called The Uses of Instantons. So that's basically what that means. And a wormhole, for me, for this talk, will be an instanton in the gravity path integral. So that's what it is. It satisfies some solutions to some equations of motion. But I want to emphasize that with the correct boundary conditions relevant for the quantity to be computed. We usually say path integral and there's some bulk action, but equally important to every path integral computation you do are the boundary conditions. And the boundary conditions depend on the particular quantity you want to compute. Okay, so this thing is going to be very essential to thinking, to my thinking. Okay, and I will always take the quantity to be computed to be defined in a non-gravitational description of the theory. This is very important to not confuse ourselves. Of course, we can be more ambitious and talk about directly the bulk theory, but you need a footing, you need a place to start. And the safest place to start is to first say explicitly at the beginning of every talk, every discussion, this is the quantity, this is the number we want to compute, and then go from there. Okay, but I want to emphasize that even though the title of this talk is taken from Coleman, I will not be using this word wormhole in Coleman's sense. So Coleman and Strominger and Giddings had some papers in the mid-'80s in which they were thinking of wormholes as inducing some bilocal interactions between Minkowski space, between Pounce and Minkowski space. So for them, the arena was Minkowski space. They're thinking of particle physics. And somehow you have these quantum gravity effects that are wormholes. And they were basically thinking of them as some bilocal operators. That's not my perspective. That makes it seem like wormholes are some small correction to the Minkowski dynamics. Here, wormholes will be on an equal footing to other putative saddle points in the path integral. Okay. So that's the philosophy. That's just one thing I want to get straight. Okay, so let's start. So let's think about what are some of the quantities that have been amenable to attack by wormholes in the recent years. So one such quantity, which we also heard about yesterday, is the spectral form factor. Just to be very clear, how this quantity is defined is an analytic continuation of the partition function. Or you can set beta to 0. So this is some kind of Lorentzian quantity. It's like a double sum over the spectrum. And so a double sum over spectra also appears in things like the 2-point function, like thermal 2-point functions contain a double sum over 2 energies. So this is supposed to mock that up, but you sort of forget about the matrix elements of the operators, and you only keep track of sort of oscillating exponentials. Okay. So this has terms like sum over NNM, e to the minus IT, En minus Em. Okay. You can set beta to 0. Okay, so this is what this quantity looks like. So let's just think about the various features of this graph. So when time is 0 and beta is 0, we are just doing a flat sum over the whole spectrum. So you get something like e to the 2s, where s is the entropy. So I will be thinking of a finite dimensional Hilbert space of dimension e to the s. So it starts out very big because s is big. But all these oscillating phases are going to start killing this quantity very rapidly because it dephases very quickly. So it starts to decrease. It could be an exponential decay in time. So, so the actual function will look like e to the 2s, e to the minus t maybe. Or it may be e to the 2s times t to the minus 3, like some power law decay. But the important point is it's decaying in time. So there's a big factor, but it goes down in time. Yes. Yes.
You have log states on both axes. That's what you were assuming.
Well, I haven't really been very precise about the thing, but I marked here just one point in time called e to the entropy, because that's the only one will be relevant here. This point is non-universal, and I'm not going to care much about it. But the point, the only thing I want to emphasize is decreasing in time. Yeah. And so if you think of black holes, the naive saddle point at some finite temperature is a cigar. So you can consider matter loops on the cigar or 1/n corrections. All of them will decay in time. All these contributions, 1/n corrections, matter corrections, all decay in time, either like an exponential or a power law or some other complicated thing. I don't care what it is. Okay, now you get to times such that these two terms start competing with each other. So think of times that are exponential in the entropy of the system. So beta is the scale. So think of times that are, let's say, beta times e to the s. There should be a beta here setting the thing. Okay, fine. The discovery is that there is a wormhole contribution which is suppressed by e to the 2s, so it's e to the 0s. Okay, so you might think it's small, but the non-trivial fact is that it has a positive power of t multiplying it. So that makes it qualitatively different contribution. So at late enough times that we don't normally think about in normal EFT, in effective field theory, we don't think of times that are exponentially long in the entropy. Okay, and then what you realize that at some point, this double cone wormhole will take over this decaying piece. And okay, so that's a contribution from gravity, and this is calculated by Saad, Schenker, and Stanford. Not the JT gravity paper, but the paper before that. Now, why is this good? This is good because random matrix theory people have predicted that whenever you have GUE statistics, whenever neighboring eigenvalues in a Hamiltonian have GUE statistics or your system is chaotic, this linear in T is very universal. In Fourier domain, if you Fourier transform this signal, it leads to the so-called sine kernel. And I encourage you to look that up. And the sine kernel has a linear piece, and then it stops. Okay, but let me go on. So that's one use of the wormhole. Like this simple kind of wormhole, it's not actually that hard after you realize what's going on, is the first use where it gives a small but increasing in time contribution, which is consistent with very general expectations from random matrix theory, which we expect to apply in any chaotic system. Okay, so what's going on here? This is not really the purpose of my talk because, but I want to say that this sharp transition from a linear ramp to a flat plateau in random matrix theory can be captured by also a semi-classical effect known as this Andreev-Altshuler instanton. Or if you think of random matrix theory as being dual to non-critical strings, like people were thinking about in the early 90s, this transition would be a contribution from ZZ brains in non-critical string theory. Okay. Yes. Yeah.
Sorry. Is the double cone geometry singular at the cone?
No, that's my next point here. It's a complexified geometry. So I don't know. I didn't really call Google for help, but somehow my phone thinks I did. So, so integrands and path integrals are complex analytic functions usually. Feynman did this beautiful thing where, or Dirac, they reduced all of quantum mechanics to basically an integral. If you do the right integral, you get the answer. But it's a complex analytic function, the integrand. And so the path integral, one can think of it as a contour integral in some high dimensional space with a defining contour. So there is some defining contour, but the saddle points that contribute to the answer for that integral need not lie on the defining contour. This is very well known just if you do one-dimensional integrals. Saddle points don't have to lie on the defining contour. What that means is that one should not really tie ourselves into picking geometries with one signature or another. Like if you have some complexified metric space and you specify your defining contour some way, there's no way to rule out complexified metrics as giving contributions to some quantity that you might be interested in computing. And this double cone is a non-singular geometry, but it's complex. And that's fine, because we know that complex things, complex saddle points do contribute to integrals. Yeah.
Just to be very clear about that, if you were powerful enough to do the integral on the contour, it's perfectly fine.
Yes.
Small corrections.
Yeah. Yeah, I agree. And I was going to erase that board and exactly do an example. So it's great that we are anticipating the next things in the talk. So let's do an example, a very simple example of this phenomena just to drive the point home, which is actually also, I wrote that here. There may be multiple ways of evaluating the same integral. You can do n integrate on Mathematica, on the defining contour. Nobody's going to prevent you from doing that. You could deform the contour, go to a saddle point, and maybe have some analytic handle of doing the same computation. And this theme of there are multiple ways of evaluating an integral is going to show up maybe a few times in this talk. Okay, but I want to do one more thing. So let me erase this stuff now, which is to emphasize the fact that the quantity to be computed matters. So here we have a wormhole which kicks in at a time of order. It's not clear when this starts to become important. That's non-universal. It's related to this so-called Thouless time in random matrix theory. But let's say you were at a time of order beta e to the s over 2. So definitely you're in the ramp phase of this quantity. Some other quantity I can plot in red. Let's say in the black hole context, it will be some von Neumann entropy. So let me plot S von Neumann as a function of time of, let's say, an evaporating black hole, or taking Samir's construction of the eternal thermofield double state, but evolving both sides forward in time. It doesn't matter. You get some entropy that's increasing in time initially, and then there's a transition to either it becoming flat or going down. Okay, so this is the plot. Like this is like quantity 1 or quantity 2. So the point is something is happening at this point, which leads to some sort of a transition. This time is just beta times s. It's not e to the s, it's s. So here already you have two quantities. The spectral form factor, the wormhole was taking over at a much later time. Whereas in this von Neumann entropy calculations that people have done, the wormhole contribution sort of takes over at a much earlier time. It's still big because s is big, but it's not as big compared to beta e to the s. So what I'm just trying to emphasize is that this quantity to be computed matters, and we should try having a discussion of theories as somehow that one picture of some saddle point is going to compute everything in a given theory. That may not be true. Like different quantities may require different classical, semi-classical pictures to be computed. Okay, so now to go to some example just to hammer the point home that let me do this integral. Integral minus infinity to infinity dx e to the minus x squared over 2 cosine of kx. Okay, so let's plot this. I didn't put e to the ikx because it's complex, so I just want the thing to be real so I can plot it. So it oscillates, decays. And of course, you could say n integrate Mathematica, compute this integral, you'll get a number. In the complex plane, in the x plane, this is the defining contour here. And now let's write this as e to the ikx and take the real part later. We see that the saddle point will be at x equals I play. The saddle point is here. Okay, so it does not lie on the defining contour, some complex saddle point. But the point is you can deform the contour to go through the so-called contour of steepest descent through the saddle point. Because of Cauchy's theorem, you can deform it to pass through the saddle point, and on this line, the oscillations go away. It just looks like a Gaussian, and then you just do that integral. Okay. Okay, that's like the basic point. The other thing I want to show also from a toy integral like this is that different quantities computed in the same theory can have different saddle points. So different quantities in the same theory may be computed Okay. Example, the same thing. So imagine like the dumbest integral you can do in this context, just the Gaussian. Okay. So the saddle point for this guy is at x equals to 0, right? Let me put an n here. N is some big number controlling the saddle point approximation. So I might say this is a theory and it has a saddle point at x equal to 0. And if I'm computing things like dx x to the fourth e to the minus x squared over 2 times n, the saddle point and the perturbative fluctuations around it are kind of good enough to give me some answer for this integral. But what about, so this is the expectation value of the operator x to the fourth. What about the expectation value of x to the n over 3? Okay, so now I have an operator which kind of has this n in it. So you're going to have x to the n over 3, e to the minus x squared over 2 times n. And you can already see, because of this n in the exponent, that the saddle point is going to shift. It's e to the n over 3 log x minus x squared over 2n. So the saddle point equation is n over 3x minus xn equal to 0, or x equals 1 over square root of 3 or something. So the point is, if the quantity you're computing has some large parameter in it, like a time of order beta e to the s, it can change the naive saddle point that you might have thought is the theory, or is like the vacuum of your theory. Like here, the vacuum got shifted, like the vacuum, whatever you mean by that, got shifted from x equal to 0 to x equal to 1/3, 1 over root 3. So that's just things to keep in mind, that Wilsonian effective field theory is fun and good when you're computing 4-point scattering, 5-point scattering, 10-point scattering. If you're computing e to the s point scattering, it may not be, you might have to rethink what the Callan-Semanzik equation is telling you about that. Okay. So those are just some generic points, and I wanted to emphasize them because in many conversations over the past years, these seem to be sort of the points that were kind of the sources of certain confusions. Hopefully. I should pause for questions at this point, like if there are some. Yeah. Well, no. There's no direct analogy. I'm just trying to say some basic points.
Okay.
So this is relevant for the spectral form factor because the double cone geometry is complex. So some people worry, oh, this is just some Euclidean calculation. What is the Lorentzian interpretation and things like that? I'm basically trying to say that Euclidean and Lorentzian metrics are part of the same complexified metric space. So one should maybe not have too much anxiety about having I's or Euclidean and Lorentzian things in the game. That's okay. And this point was just to emphasize the fact that these transitions are happening at times that we don't normally think about. Like the StatMech people or the dynamics people are used to thinking about them in the context of, say, Poincare recurrences, things like that. Like when you take times of order entropy, scaling with the entropy or exponential of some weird things can happen, and like effective field theory usually does not give you a good description of those quantities. May not.
So, thank you.
Okay, very good. And of course, I don't need to emphasize to this audience the fact that instantons are very useful in quantum mechanics. We compute, the splitting of the double well potential using that. We compute barrier tunneling. And both of those things can also be computed using other methods, like solving the Schrodinger equation, for example. Okay. Okay, so I think I have done all of these. Okay, so I discussed the spectral form factor. Let me discuss another quantity that I think is maybe much more closer to what people think about. So we'll think about a 2-point function, phi of t, phi of 0 at beta. I want you to think that phi is some boundary CFT operator. Okay. So one thing we expect is that this thing should decay in time because it's a thermal state of some. But how do we compute it? Again, let's say we are in ADS2 to make life simple. So thermal correlators are related by analytic continuation to these Euclidean correlators. So this is H2, the disk. I have these points separated by some time tau, and it's computed by some geodesic. So if this operator is heavy, let's call this G of t. G of t is e to the minus mass of phi times the length of this geodesic. And if you work it out, it becomes 1 over sine pi tau over beta, beta over pi to the 2 delta, or 2 times the mass. Okay, so you might say this is not exponentially decaying, but tau is related to t with an I. So when you change it to t, it becomes a 1 over sinh t to the 2 delta. And at late times, this goes like e to the minus t times 2 delta. Okay, so you get this exponential decay from computing geodesics in the black hole background, right? The H2 disk, this is supposed to be some version of the cigar, like the radial and the theta directions of the cigar. 2-point function decays in time. Now, again, by very general arguments having to do with the discreteness of energy levels, you can show that in a system with a finite number of states, this 2-point function cannot really exponentially decay in time forever. Just because this is a sum over n and m of n phi m squared and an oscillating factor of the type that I wrote before, e to the minus it, en minus em. Pardon, I'm not writing all the beta factors and stuff because they're not important. The point is this kind of oscillating sum appears again, and if n and m are discrete, this is a quasi-periodic function. This is inconsistent with having this kind of a spectrum. Okay, so we can ask. There are 2 options. Either resolving this problem of this exponential decay will be amenable to wormholes or not. Like a priori, you don't know. Is there a wormhole that can give a contribution that is consistent with this formula and not with this formula? It doesn't have to reproduce the details of it, but we can ask whether there exists a wormhole that will lead to, let's say, an increasing contribution in time, a contribution that does not decay with time. Okay, so a priori, we don't know, and Maldacena wrote this paper in the early 2000s where it was a question. Can we find some description of how do we resolve this puzzle? And again, like the surprising result in the last few years was that yes, even this 2-point function quantity, which is very natural, observable in the boundary theory, does have wormhole contributions that are non-decaying. So G of t computed using holography, by which I mean computed using gravity, has non-decaying contributions at late time.
Communication générale. La direction vous informe que le CEA Saclay procédera à un essai de sirène, aujourd'hui à 12h15. Un signal modulé spécifique sera émis pendant 1 minute et 40 secondes.
Every Wednesday, the first Wednesday of every month is a nuclear drill. So there's an alarm going on at 12:15. So
Okay.
it's going on the main center, so you're not here too much unless you stay over here. You don't get to use that in cover. No. I think some people have to do stuff like that, but people don't.
Okay, so how do we, let me put some more pictures on this thing. So we know that this 2-point function is analytic in the complex time plane in a strip of width beta. So this is real time, this is imaginary time. Here I've drawn a strip of width beta. And we were trying to compute that function staying on the top boundary of that strip. It's slightly more convenient to move to the middle of the strip. So because this beta will stay of order 1 and we are taking time to be large, the decay properties don't change very much, whether you put the point here or here. But what's nice about this point is that it has an interpretation in the thermofield double state, this latter function as being computing a 2-point function between operator here and operator here. So this will be T over 2. This will be T over 2. Okay. So instead of computing sort of a one-sided correlator, we are just computing a two-sided correlator. And again, if the field phi was heavy, this will be given by some geodesic. This geodesic that goes through the wormhole, through this Einstein-Rosen bridge, grows in time. The length of the geodesic grows in time just because we've seen this of the stretching of these slices. The nice slices that go through the wormhole stretch in time. And the consequence of that is that the length of this bridge becomes longer and longer as time goes on. And the correlator was e to the minus m times the length. So if the length is growing, this correlator is decaying. Okay, so we have related the decay of this correlator to the increase in length of some geodesic under this forwards time evolution on this geometry. And the point is that if you really draw this out, it's helpful. Like there are these pictures in Misner-Thorn-Beater that are nice. So the Penrose diagram somehow hides that. So if we draw this cross section, the wormhole is fat and looks like that. There is the bifurcation surface, but at late times, it kind of becomes longer and skinnier. So the bifurcate points are moved out, like because this slice intersects the horizon at 2 points. Those are these, and then in the middle, it's kind of short. But the length we are computing is the thing that's kind of threading this Einstein-Rosen bridge. Now, what is the effect? What is the effect that we want? So we want some effect that this length of this wormhole should shorten somehow. Like if there was a quantum gravity fluctuation in which the wave function of quantum gravity has support on all kinds of geometry. This is just some classical metric we write down as the dominant one. But there can be processes in which, just quantum processes in which this wormhole length is shortened. And it was shown in a paper by Saad, a single author paper also from 2018 or 19, that these effects do happen in a model of gravity called this JT gravity. And if I draw this next to this, so this disk and this geodesic and its analytic continuation was drawn there, but what he considered was a disk, but with a handle. So this is now the Euclidean picture. So now, instead of considering this geometry, consider a geometry that's a disk with a handle. So this is suppressed by genus counting. because this geometry has a higher genus. So this will be e to the minus s suppressed because of the handle. But now you have these points, these 5 points, and the geodesic can sort of go through this handle. And there are other geodesics here. Like there's this geodesic that doesn't enter the handle, and there are geodesics that enter the handle. And the result of the computation was that the geodesic that enters the handle is the one that gives this non-decaying contribution at late times. So the whole contribution is suppressed because it needs the quantum gravity path integral to produce an unlikely fluctuation, the unlikeliness of having a handle. But you have to compete that against increasing in time contribution because, the wormhole can get shortened through this emission of a baby universe and absorption. So in this language, this emission of a baby universe and absorption is nothing but attaching a handle to your disk. But anyway, the point is you do this calculation and you get something which is not decaying in time exponentially, it is increasing in time linearly, much like the ramp in the spectral form factor. Yeah.
For this one boundary case, what's the the simple geodesic that doesn't go through the handle? What's the analog of the growth of the decay in time? So the two boundary case, you have this long wormhole. Here it's what?
Well, so here I was trying to motivate it using this picture.
Yeah,
if the time is very long,
yes,
then you don't expect that thing to depend whether the point was on the top boundary or on this boundary.
I just mean in this one boundary case, the original contour, what picture would you draw to show that as time goes on, the naive path gives you a decaying
I don't
contribution?
have a picture for that. I only have this formula because this tau continues to t, and then because we don't have geodesics in ADS that connect 2 points on the same boundary. Like you just cannot have a geodesic that goes out from the boundary and comes back. So there are certain configurations in which if you're trying to compute correlators using geodesics, you have to rely on analytic continuations. Right? Just because the geodesics bounce back and forth, and you cannot have a geodesic. You don't have geodesics that kind of do this. This is not a configuration. Does that kind of answer your question? The short answer is no, like you just have to compute it here and analytically continue. You could say the words that there is thermal noise and it decays in time. That's some real-time argument because it's a thermal state. And okay, very good. So these are sort of more correlation function type observables. And since a lot of the attention in this community and also,
So in this last example where
Yeah.
you have the geodesic going through the wormhole, so the expectation is that the just from finite systems quantum mechanics is that the thing's going to exponentially decay and then it's going to plateau at some small value. So how do I see from this picture that it is going to plateau and what the value is at the plateau?
Well, so in the spectral form factor plot, like this thing does not give the plateau, it gives the analog of this ramp. Because even in the 2-point function, you can show that there is kind of a ramp before it plateaus. And this, how to get the plateau is more complicated. That is not like a simple wormhole effect.
Okay.
Which is why on the spectral form factor, I kind of showed that thing called the Andre-Waldschüler instanton.
Okay, so this is the analog of the double cone
Yes,
in the spectral
yes,
form factor.
yes,
Okay,
yes.
thank you.
Yes, because it's an effect of the same genus suppression, e to the minus. Yeah.
So, sorry, this is probably my confusion. I got a bit confused with this red curve that you said doesn't exist.
This one?
Yeah.
This is
but,
not a geodesic.
But I thought, well, I mean, you could compute one-sided correlator, unequal time correlator by just computing space-like geodesics in ADS. Is that not true?
Unequal time?
Yes.
Real time or Euclidean time?
Real time.
No. I mean, just there is the geodesics in ADS bounce back and forth, right? There is a potential barrier and it cannot get out. What you have is that geodesic. So if you drew the Euclidean section on this figure, that disk would kind of look something like coming out of the board and going in. So the disk kind of sits like this. So if your points were Euclidean time separated along the circle, yes, there is a geodesic, but in real time, there is no geodesic.
Okay, maybe we can talk later. It's fine.
I have the spatial separation to 0.
Oh, okay. Now I understand.
So it's,
All
it's
right.
time like separated on the boundary. If it was space like separated on the boundary, then yes.
Okay, okay. Now I understand.
Yeah.
If I will start to put handles on the cigar,
Yes.
would the 2-point function grow in time?
No, this is a handle on the cigar, right? The disk is the cigar.
Yes, yes, but
Yeah.
suppose now I start to calculate quantum corrections on top of this.
On top of this,
On top of the cigar.
This one?
Yes.
what kind of quantum correction you mean?
1/n corrections.
1/n corrections, okay.
Would they make the 2-point functions grow?
No, no. The 1/n corrections don't do that.
Okay.
E to the minus n corrections do that. Like you need things like this. Because you need the geometry to change drastically in order for you to have shortcuts like this. Okay, so I hope I have tried to convince you that these wormholes are kind of a useful computational technique. They're not getting everything, all the details right. Like the spectral form factor that I drew, I kind of elided a very important point, which I drew this as a smooth curve, whereas you saw the numerical plots in Arnab's talk yesterday, there is all this random noise here. And this double cone wormhole does not produce this noise. It produced some kind of smoothed out version of it, but that's better than having something that's decaying in time forever. So it's going one step beyond the cigar, but it's not going all the way to giving you the right answer for n equal to 4 super Yang mills. So it's an improvement over what we knew before, but it's not the final story. No, just the ramp. Yeah. The transition from the ramp to the plateau has to do with the genus expansion in string theory diverging. Because you have 1 handle, 2 handle, 3 handles, and that series diverges. And at late times, like this ZZ brain sort of comes in and has to, do something to that perturbative expansion. So this kink here is related to sort of de-instanton effects in string theory. Okay, very good. So now let me discuss this von Neumann entropy, because that's has its own set of confusions in even what the quantity that we are computing is. Sorry? There are not.
These effects you're talking about, I mean, it's an analogy between the matrix model you would use to compute this and the matrix models that were considered 30 years ago. So in the matrix models considered 30 years ago, they were actual d-instantons.
These also have them.
These also have them, but it's a difference between e to the minus of n effects and e to the minus n effects.
Okay,
e to the minus e to the n effects. So it's not an actual d-brain instanton in string theory. It's because of the difference between the L that people talk about and the matrix model that computes this versus the n, they're related by L is e to the n.
So let me say some words about that. I think they're exactly the same in a very precise way. So, okay, so pardon me, like this next maybe 3 minutes will be for people who have seen this SYK model and so on before. So there's an n in the SYK model, which is the number of Majorana fermions. So you have chi1 through chi n. In JT gravity, handles are suppressed by e to the minus n. So if you want to think of this 2D JT universe as a string, then e to the minus n is the string coupling. And therefore, d-brain effects are e to the minus 1 over g string effects, which is like in this n languages, e to the minus e to the plus n. But this is the level of the effect that gives you this Andre Walschuler instanton. So this sharpness of the thing, the ramp is computed by this, but the transition from the ramp, this sudden abrupt stoppage of the ramp and going over to the plateau, that's an effect of this size, which is like, so it's the same, right? So we agree? So this is like what we would call the d-instanton in string theory, and this is what this is. Okay. 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 All right. Any question? Is it?
No, let's see it. Let's see it.
Ouch.
No problem. Everything worked out?
Yeah. In the equations you just wrote about the SYK, yeah, and so on.
Oh yeah.
So I understand that they're the same thing, but running it the other way around, like if we interpret G string as e to the minus n, should we think of G string in string theory as counting degrees of freedom, right? Because this is not the
No. So that's what I'm saying. So you should not. But the point is, the mathematics of this side is precisely the mathematics of string theory. And it just, if you didn't know about the SYK model and you were just doing JT gravity, like JT gravity, you might just have called this thing suppressed by some number, right? And you would not relate it to an exponential of something else.
Yeah.
Right. So in the matrix models that were studied in the 30 years ago, the n was not the number of fermions. The n was the size of the matrix, which is the dimension of the fermion Hilbert space, which is exponential in n. So the n from 30 years ago is is the dimension of the Hilbert space, whereas here n is the log of the dimension of the Hilbert space. So dim h is like 2 to the n over 2. Right. So that's like this extra exponential. It's just what you call n.
Yeah. Mathematically, I agree. I was just wondering if this we should think of.
No, you should think of like, if you think of the random matrix models that were dual to this minimum, the non-critical string is dual to some matrix integral for c less than 1. The matrix integral has some dimension of the matrices. If you thought of that matrix as the Hamiltonian of a system of particles, like some nuclei, this n would be the number of those nuclei, whose Hamiltonian is that random matrix that was talked about 30 years ago. That's the only difference, is whether you're counting nuclei or you're counting the dimension of the Hilbert space. Okay. Very good. Okay, so now we come to von Neumann entropy. This is like a really thorny thing. So I would like to just set some common ground, perhaps just for later discussions over lunch and things like that. Okay, so I would like to draw a table, which I think Nick has seen before, but I will draw it here again. So, okay, so I hope everyone's familiar with the definition of von Neumann entropy. You have some density matrix rho, and von Neumann entropy is trace rho log rho, negative. And in certain contexts, this rho might arise by tracing over a set of degrees of freedom outside your region of interest, or rho might just be the thermal density matrix. I don't really care. So rho could be rho thermal of your full system, or rho could be tracing over some B of the full system density matrix. It doesn't really matter. It's like some density matrix we are interested in. Okay, so in the literature, there have been various prescriptions in the gravity side to compute these entropies. Okay, so we have this Bekenstein-Hawking they just said the entropy is area over 4G. Well, the 4 was not known, but Bekenstein, using some arguments, could argue that the entropy should be proportional to the area. So that was just some general argument. Okay, so that's just a rule. I give you a metric. It's a classical solution to Einstein's equations. You figure out where the horizon is, compute this number, and you say that that's the entropy. Okay, so this was in the 70s. Let me jump quickly to Ryu-Takeyanagi formula. It was a conjecture at the time. Ryu and Takeyanagi also said that in ADS-CFT, if you trace out a subsystem of the boundary, the entanglement entropy of the remaining region is given by an area over 4G. where A is some extremum. So you extremize this quantity, and the von Neumann entropy is equal to this. Let me just say one word. So if you have ADS3, and the boundary is a CFD2, so this is a spatial slice. Let's say this is our region of interest. This is region A, this is region B. You pick a candidate region here, like this. So you're extremizing over the red things. And the final extremization curve, its area over 4G, will give you the entropy of rho A. Okay. This thing continues. So this was in 2006. The next thing was this quantum extremal surface thing. This was discussed by Engelhardt and Wall. I didn't write the year, but it's like a formula like this, but where you extremize a different thing. You extremize A over 4G plus some S, where S should be thought of as the entropy of the bulk fields here. So the bulk has gravity, but it also has fluctuations like the gravitons and matter and so on. So this S here is the entropy of this stuff when you trace out the other. Okay, this is just some formula. You can think they just pulled it out of the hat, or they arrived at it using arguments like Bekenstein was using about the generalized second law and stuff like that. Okay, this quantity had already appeared in Bekenstein's work. This area plus the entropy of the matter outside the horizon. So anyway, so these are some heuristic things. Okay, these are not very precise. And the most recent avatar of this was this so-called island formula, which is a naive, which is a generalization of this, where you say that you should allow for compact regions that are not connected to region A. So if you let your extremization not be over things that are just continuously connected to the region of interest, but let your shaded region consist of disconnected pieces, and then extremize this. So this is just like a simple extension of this thing, which says, don't forget about these compact pieces. Maybe sometimes they will be important. So this was also heuristic. So this is all some heuristic side. A critic would have a good reason to believe that maybe these are not fundamental. Okay, that's fine. But now we come to the second side of this table. There is, for each of these, an underlying path integral. It's a path integral of the sort I said in the beginning. It's a gravity path integral with some very specific boundary conditions. The boundary conditions and talking about them and discussing them is as important as talking about the saddle points themselves. Here, we of course know that there is this famous Gibbons and Hawking work from 1977, which justified this, right? You do set up the boundary conditions for computing Z of beta. And maybe one should really put here Witten 1998, because in the context of ADS-CFT, it's really made very precise. You're computing a partition function of the boundary theory at temperature beta. You set up some asymptotic boundary condition called S3 times S1. And then you fill it in with whatever you want. So you're using ADS or flat space metrics as a crutch, as a way to compute saddle points in the boundary theory, right? So I'm really interested in the boundary theory, and I really want to compute that path integral, but I can't do that. So I do this ADS-CFT master field. I come to the gravity picture, and the cigar or the thermal ADS are just saddle points to compute this integral. Here, the corresponding derivation was given by Leibowitz and Maldacena in 2013. So this was like a 7-year gap where people were just using this formula, trying to test it, do various things. But 7 years later, that these authors realized how one should derive this. Now, the point of this paper is the fact that you're computing a boundary entropy. This rho belongs to, the bounded operators on the Hilbert space of the CFT. It is not a bulk object. So the thing you're computing is a boundary von Neumann entropy of some region. So therefore, you compute it in some way. And one of the ways people like to compute it is via the replica trick. So instead of computing rho log rho, you compute trace rho to the n, and then take n to be 1 plus epsilon. Okay, that's the thing you do. With n, it becomes simple. So the boundary quantity trace rho to the n is computed on this so-called replica manifold. So you put the QFT on a replica manifold, and you do that path integral. We want to do the n equals 4 path integral with boundary conditions that are relevant to this, quantity. And then Lukowitz and Maldacena basically said, that's your boundary condition. Fill in the bulk with whatever smooth ADS metric you can that's consistent with those boundary conditions. You're not replicating the bulk. You're not tracing out over anything in the bulk. You're tracing out this boundary region. And that sets up some replica manifold on the A part of the boundary. And then the ADS space that fills it in is completely smooth. Yeah.
Do you know if the sufficient condition for the Carlson's theorem that guarantees that the analytical continuation is unique?
No one knows that. This is like where you try, you shoot for something. Like the state of the knowledge is not nearly precise enough to be able to apply those theorems. So you try to do your best. And if you get a reasonable answer.
So would you call it a rigorous derivation?
No.
Okay.
I mean, in this business, nothing is rigorous. Like, it's just like you follow your nose, you do the simplest thing, and if you land on your feet, great. If not, okay, think about it again. Here, a similar derivation was given by Dong and Lukowitz. And here, it was in these papers by PSSY, and this was also 2019. So I was part of this work, but not part of this work. So in some sense, this column is really the more fundamental. One should not really treat this island or these surfaces as being, fundamental objects. You're really computing some path integral. And in some cases, the answer to that path integral happens to be a simple thing like area over 4G or extremization over this island, whatever thing I would write down here. So it's kind of wrong to assign a special significance to the fact that people here have drawn, not only here, but like, pictures like this, where you have an evaporating black hole, and you have some radiation region far away, and you kind of draw a picture like this, where this is like the island, and this is like the radiation. And there have been evocations, because this came a few months after that. And already, like, it's kind of funky. Like, people think there's some non-local effects. The island is being transferred to the radiation. Or maybe there is some unitary that's acting together and transferring the information from the island to the radiation. Nothing of that sort is being claimed. The only claim is that if you do this replica trick on the boundary, and you do the bulk saddle point analysis, and you look near this n equals 1 plus epsilon limit, the right column, this fourth entry, will reduce to this. That's the only claim. So, for example, we cannot compute rho radiation ij, right? Where I and j go from 1 to dimension of the Hilbert space. Nobody is claiming to have a computation of this, because to say that you've solved the unitarity puzzle of Hawking radiation, you really need to compute this, but we are not computing this. The page curve is only one number. So trace rho log rho is one number built out of these dim h square quantities. Okay, and it's a necessary condition that the entropy of the Hawking radiation follow the Page curve, but it's not a sufficient condition to have unitary evolution. It's very easy to have two density matrices, rho 1, let's say being 1/3, 1/3, 1/3, 0, and rho 2 being 1/4, 1/4, x, and 1 minus x. And we can solve for x such that the entropies of these two are equal. But there is no unitary evolution that will take rho 1 to rho 2. Because under unitary evolution, the eigenvalues of rho must be preserved. So rho 2 cannot equal u rho 1 u dagger. But S of rho 2 might equal S of rho 1.
Okay. In this text or this story, though, there is a statement, a Lorentzian statement about the fact that the entropy goes up and then it turns over, and the different saddle points dominate the path integral, and that's a Lorentzian statement that at the page time something happens. There's a transfer between saddle points. So
but that's a boundary time.
Sorry? That's
a boundary time. That's a time a bit like this, right?
But okay, but are you throwing the whole Lorentzian evolution story under the bus at this point, or are you just saying that it's only Euclidean? And
well, what would you say here? So here we did a Euclidean computation that came out as a function of tau, and then there was some method to get the answer for the real-time Lorentzian observer, like here, right? So this is the sort of procedure that's being followed. So you define the state and its evolution on the boundary. So that time is a boundary time. And these replica manifolds are sort of complexified saddle points, which have sort of this tau and t kind of going together in some sense, yeah. So that's the sense in which the Lorentzian and Euclidean are kind of unified in the space of complex metrics. Like there isn't really a separate question.
But how do I tell which saddle point dominates when?
Well, we do the computation. So when you compute like the actual action of the saddle point, right? One of them, those actions depend on time. And so you just compare, like is I1 of t bigger or is I2 of t bigger? And one of them will be bigger than the other. And
isn't that putting in the answer you want to get rather than?
No, because I1 of t is computed by this integral. It's computed by integral dg e to the minus integral d4x root g r minus 2 lambda with the boundary conditions. Nothing is being put in by hand. Like this is the starting point. This is the thing you compute. And sorry? Yeah, but the important point is the boundary conditions, because the action, the on-shell action of some saddle depends on the boundary conditions, because it's crucially input this boundary condition. And this is what you're computing. So I1 of t and I2 of t are outputs. They're not put in by hand. Yeah.
So the closer the complex saddle is to the Lorentzian section, I would imagine the closer it is to one's picture of what's going on in the real-time dynamics. So are these auxiliary saddle points that give you the page curve coming down, are they saddles that are really far away from the Lorentzian section so that it's hard to infer from them what's going on in the Lorentzian dynamics?
Yeah, I would say so, yes. Because like, for example, in the case of the cigar, right, the cigar is kind of 90 degrees away from the Lorentzian section. And these are pretty similar to that. So, and I should say that when it would be great to have some kind of real-time dynamics, but I would say that what that means would be solving the Schrodinger equation of quantum gravity. It will not take the form of some modes propagating on the Schwarzschild geometry cigar. Like, because we've seen that, because it's quantum gravity, so this space-time fluctuates. This is just a classical solution. You might have a configuration where a 3-metric where there is not even a horizon, or there are some crazy things going on. Somehow the quantum gravity wave function is delocalized over those geometries. And to capture the things like this 2-point function or the von Neumann entropy at late times, it's important to study that object, the quantum gravity wave function, not some dynamics on the cigar geometry itself. And I think that's actually consistent with the fuzzball idea, because we would like not just to get a smooth time going up and a smooth thing going down, or this ramp which is completely smooth. One would like the noise. And the page curve is also some average curve. Like if I have a complicated many-body state, its entropy curve, if I trace out a part of the system, is not going to look perfectly straight and then perfectly straight down. There's going to be some wiggles and oscillations, some detailed form, which are not captured by this replica wormhole. So again, there is room for these fine-tuned adjustments to come in. Like, so if you have some fuzzball state, that might be like one of these microstates that Vijay was talking about. And if one could compute in that, one would get all this noise and one would get a much more fine-grained signal.
Well, that's assuming the geometry would have the requisite resolution.
Yeah. So when I said
to
fuzzball, I
those.
meant this quantum fuzzball, like not the microstate supergravity solutions, but whatever we imagine the most general quantum fuzzball
Sure,
is. That's what I meant. So that's not a geometry, right? If I
Not for me. But,
yeah, okay, yeah, exactly. Yeah.
But you should talk to other people.
Okay.
I guess you should try to wrap up.
Yeah. Well, I'm wrapped up. Well, that's it. So I would like to just emphasize again that these wormholes are kind of computational tools. No claim is being made that they're a fundamental theory of the bulk. You need string theory eventually and brains and all that complicated stuff in the bulk. But the simple geometries are a way of capturing some effects that go beyond the cigar geometry. It's rather surprising that these e to the minus s times linear in t effects can be computed. So that's like the new thing. The new thing is that you can do more than Gibbons-Hawking. Instead of just computing some rho of E, which is, by the way, itself an average, you can compute the 2-point function of rho. Like that's this ramp, right? The correlation between eigenvalues is the ramp. So it's just like one step more than Gibbons-Hawking were doing. And that's basically the message, that wormholes are useful, and this is semi-classical gravity. Nobody's claiming that it's the ultimate theory of the bulk. That's probably involves strings, and nobody has that. But that's why the title of my talk was the uses of wormholes. Like, they're useful if you are interested in these specific quantities. Okay, thanks for your attention.
Thanks a lot, Raghu, for a very nice talk. Maybe time for one more question, and then we ask them over lunch.
Vijay has a
Vijay.
Where is it? Ah, okay.
So that was really great. So at least some of the practitioners of the art, wormholes, will draw pictures which involve, in the Lorentzian section, things like this, some sort of doubly holographic setting where there's a wormhole running from radiation to the inside, and then words get said about how indeed operators acting on one side act on the other side. Do you have any comments about that kind of thing?
Well, all that stuff, for example, in this Pennington Starr Schenker paper, something like that happens. But again, if you make that final statement, that's like something on this column. So if you say that, for example, this complex PETS map can create some excitation in the island, that has to be backed up by a path integral calculation on this side, which they did in that paper. So the PETS map calculation of,
but going
also,
back,
yeah.
Sorry, you finish.
So I'm saying, whatever question you ask about this setup, I will only, believe it, the question and the answer, if you can phrase it on this side and compute it on this side. Otherwise, it's just a bunch of words.
Yeah, so I totally agree with that with that comment. Yeah. But my question is, with regard to those kinds of computations where there is a action of an operator on a supposed disconnected region,
yeah,
which produces an effect on some other
Yes,
disconnect region.
Yes.
That certainly I find unnerving and interesting. And you seem to be saying specifically that there is no claim that that kind of thing can happen. So I
No,
don't
no,
quite
no, it can
understand
happen
that.
because they explicitly did a calculation like this. So
Right.
they set up the computation on the boundary that was, doing this. Essentially, what that amounts to is the following. So let me just say a few words. Say you have a Bell state. It's a very simple statement at the end of the day. Say you have a Bell state, 0, 0, plus 1, 1. Okay, the first qubit is held by Alice, who lives on Mars, and Bob, who lives on Pluto. And they have these 2 qubits. Okay, now let me act on this with the operator Z1. So Alice acts with the Z operator on this state. Okay, so what does that do? That does 0, 0, minus 1, 1, right? The final answer could also have been thought of as if Bob had acted on the state. Right? I mean, this is just an identity. So when you have entanglement, operators acting on one side of the system for some particular state and some particular operators can look like as if the operator acted on the other system. That's basically what's happening, because now using intuitive language, like on this side, you would say there's a lot of entanglement built up between this radiation and the interior of the black hole, and the state is kind of like this. So we should not be surprised that equalities like this are true, right? And that's what they're making precise. I mean, nobody will debate this, right?
Not now, anyway. Let's thank Raghu again.